Hello, this is Glenville Pecor, and this is a video about friction. This is about part of second law because I started talking about friction. Well, we need to know first of all, what is friction? Well, friction. This is the most important part of the graph. There's some stuff that you don't really need to focus on the graph, but I'll show you the most important stuff. Friction is related to soft surface roughness, but the force of static friction is different than kinetic friction. These two are different. They're the most important things. Friction is usually described in a standard friction model. I don't know, like you're pushing a car, you're driving a car on a road, there's friction always there. Friction usually includes air resistance, unless said otherwise. Well, these are the most common. Air resistance is one of the most common. The viscous resistance and fluid friction is another common. It goes more common, less common. So, what is friction? Well, I just kind of explained it there, but in mathematical terms, friction, the force of friction, is equal to the coefficient of friction times the normal force. So, let's say in this problem right here in this problem, you have a total force. You know the friction. I'll give you let's find the coefficient of friction. Because we already given the friction force is, oh, by the way, if you did not know, listen to the last problem. This problem is that you're pushing a friction force with 100 newtons to the right. But you have a friction force which is 60 to the left. In this box, 30 newtons. So we figure out everything here. So the friction, we know, is 60. So it's 60 to the left. With that in mind, we know F is equal to 60. We know normal force, 60 newtons. Normal force is equal to, what's the weight? Well, what's the weight? 20 plus 10 is 30. But going back to one of my other videos, how we figure out we'll transfer it to newtons by 30 times the 10, which the force will cancel out. So 30, no, it's not 30 times. Yeah, 30 times 10, you get 300 newtons is the normal force. Because there's no other force acting upon it, so we know the weight is equal to normal force here. Now, what is mu? In this problem, I'm going to make mu a u, actually, because I can't write that for some reason. So, mu, which is equal to mu, u is equal to mu. So, mu, how do we figure that out? So let's divide force by friction. Force by friction divided by the newtons. Well, whoa, the newtons cancel out. So what do we get? Let's do the math right now. So we put in your calculator 60 divided by 300. So the coefficient, which has no units, mu is equal to 0.2. So there we go. Let's also show something else that can help you prove that weight does not change friction. Let's change this. Weight only would change the coefficient of friction, but never the friction. So let's change this to, I don't know, let's change this to 0. Pretend this block doesn't exist. This isn't here. And now, since we know total force is now actually equal to 60 because you're pushing with 100 with a friction now of 60. So 60 backwards, you're pushing here. So force is still the same. Friction is still 60, so you won't change. Normal force is now 200. So what is this now? We have to do 60 divided by 200. Remember, the forces cancel out also, so the new coefficient is now 0.3. As you can see, I just proved here, weight does not change friction. What changes friction? Well, nothing. Friction will be always a constant force because of the surface. What changes friction, though, is, well, no. Pretend there's carpet on carpet here. Whoop. Now it's wood on carpet because of the box. The top of this box is made out of wood. This friction would have to change now because the force of the friction is different. And let's look at in this model right here. I'll show you. Okay, in this model here, let's go to one assumption. Right now, I'm going to ignore the bottom part of this. I don't want to show you it because it is not 100%. I don't want to show you the bottom part. But look, Pretend this is all the same surface area. Well, basically, the friction would be the same because the friction due to the surface area and the ground, that's the same. But let's say, see this almost triangle right here? This trapezoid, sorry? The trapezoid right here and this trapezoid. Let's say the bottom was carpet, the top was wood, and you're on cement. The friction would change because the surface area is way different. So let us recap. See this right here? So let us recap. So the assumption is that, oh, the surface area does matter. Well, no, not really. The surface area does not matter because, like in a lab that we did in class, basically we had a block just like one of these right here. So with this block right here, this we proved it's both sides wood, cement, wood, cement. We proved, and when we did the thing, we proved that the friction. What kind of friction do we use? Well, there's two types of friction. Static friction results when surface area of two objects are at rest. So right now, there's static friction. Well, kinetic friction, hence the word kinetic meaning, part of the word mean energy. That's when it's moving. So the kinetic energy of both the same surface parts on this will be the same. But let's say this is wood, see with the trapezoid, the bottom is wood, but the top is carpet. The kinetic friction would be different because the surface area changed. And basically, that is a summary of friction for you.